Okay, this video is a continuation of 5.1 day 2. You should have just finished the video on simplifying expressions, and now we're going to move into trig equations. A couple of things you have to pay attention to is the interval in which you're solving the equation over, and you still are going to need some of those identities. So this is a really basic direction. We're going to solve each equation over a given interval. And so my first example is going to be this. So you can see we definitely have an equation. We have the square root of 2 tangent x cosine x minus tangent x equals 0. So each side has an expression that's set equal to each other. We're going to solve for x over this interval. Pay attention to the interval. I'm including 0. I am not including 2 pi. So the first thing I look at is, do I have a common factor? Well, let me back up. The first thing I'm thinking about is this equation set equal to 0? And it is. Then I'm looking for a common factor. I can see I have this common factor of tangent x. So I'm going to factor it out. We should know from the zero product property that we can only set factors equal to one number, and that number is 0. So we're going to go ahead and set each factor equal to 0. This is a non-calculator problem, and I'm expecting you to give me exact answers. So now you're going to have to think about tangent x equaling 0. What angle makes that happen? And some of you might think of an inverse. I want to be very clear. We know that inverse functions have restrictions on their range. I am not solving an inverse equation or an inverse trig function. I am solving a trig equation, but I might be thinking of inverse. So pause the video and find the angle that makes tangent x equal 0. So we should know that that occurs at 0 in pi. The next equation, prior to solving it, I'm going to go ahead and set cosine x equal to 1 over root 2. Some of you might be more comfortable of thinking about 1 over root 2 after rationalizing the denominator as root 2 over 2. Now you're going to think about what angles will make cosine have this output, have this ratio from 0 to 2 pi. And there you have it. We have 4 answers. Okay, in a classroom environment, you know my routine. I'd say, okay, now here's one for you to try. And here is one for you to try. Sine x times tangent squared x equals sine x. And you're going to solve that for x over the interval from 0 to 2 pi, inclusive of 0, not inclusive of 2 pi. Go ahead and take a moment and solve this equation. I haven't finished the problem yet. I'm going to go ahead and finish that with you, but I want to bring up one of the big no-nos. I suspect that there's quite a few of you out there that your instinct was to divide every term by sine x. That is a big no-no. You just eliminated some of your solutions. Your goal should be to get the equation equal to 0. And when you have that urge to divide through, that means you actually have this GCF of sine of x. And so you can see here in my first step, I moved sine of x over. In my second step, I factored it. And then I set each factor equal to 0. Well, I also want to talk about this. I mean, sine being 0, I think most of us know that that's going to occur at 0 in pi. What happens with this expression is students forget if we use square rooting to solve a quadratic, we forget we have plus or minus 1. If you did forget that plus or minus 1, I encourage you to pause the video and then make a new list of your solutions. You can see we ended up with 6 possible answers I want to make sure it's clear that that's 7 pi over 4. I'm going to move into a problem that might be a little bit more challenging for some of you. I have a trinomial. In fact, it's a quadratic trinomial using trig. But I've also changed my interval. I don't have one. I'm basically saying I want every possible solution. I want my solutions in radians. Okay. So here we go. Some of you can factor and go right into factoring this problem. I think that's wonderful. Some of you might feel a little bit uncomfortable because of the sin x in there. If that's the case, there's nothing wrong with saying let u equal sin x, and we temporarily substitute for u. I do hope that at some point in time you do become comfortable and you don't need the u substitution, but it's okay. It's a tool. It's something you can use. Now we have something you're comfortable factoring. Okay, I'm just going to confirm that my factors are proper. 1, yep, we're all good. And then I set each factor equal to 0. And I'm confident that at this level, you guys can see this. Here's the problem with u substitution, what I have found in my years of teaching. Students stop here. They forget that they're not solving for u. They need to solve for x. So I've got to replace sin of x back in for my u. So we're good so far, but now we've got to think about all solutions. So let's think about sin of x equaling -1/2. Let's think about all the times in one revolution that occurs. So I know that that occurs at 7 pi over 6 in quadrant 3. And I know that it also occurs in quadrant 4 at 11 pi over 6. And I cannot combine that into one statement. If it was cosine, I could take a moment to think about why that's possible, but with sine, I cannot. How often will that happen? Every 2 pi k for both of these. Oh, and I'm going to write something like where k equals an integer. Oh, by the way, Izzy, you've heard her before in some of my instructional videos, my little dog. She is right by my side snoring. We have one more situation. We have to think about when sin of x equals -1. I could write that two ways. I could write that as 3 pi over 2. I could write that as -pi over 2. It's up to you. So I have to write these as equations. X equals blank, x equals blank. And now I can solve these. Oh, let's not forget, where k is an integer. Here's my last example in this video. You try again. 3 sine t equals 2 cosine squared t. You're going to find all values of t in radians. Okay. This one has a little extra something to it. It is a little bit more challenging. I still think that you can do it. I will give you the hint that you're going to need to think about a trig identity. Please pause the video now and do the best you can on this. I'm going to give you a little hint in case you got stuck. So I moved everything over equal to z and set it equal to 0, but I don't have a common factor and I need one. So I can't change sin t. I don't have an identity to do that with, but I do have an identity for this. So if you couldn't solve the problem, If that hint helps, pause the video and finish it now. Here's another hint for those of you that are stuck. And if you were stuck, pause the video and finish it. I have not finished the problem yet. I'm going to do that together as a class. Take a look at my work, making sure that you have gone ahead and you clean this up. Notice where I wrote careful. A big mistake students make is that subtraction, that negative there. I like to rewrite right here where I'm putting a star, that in the proper quadratic form. I factored without using U sub, if you U substitution kind of thing. If you needed to, you can. So at this point in time, let's wrap this up together as a class. Setting each of our factors equal to 0. We know that sine t can equal 1/2. We know that that will happen twice in a revolution. We know that it will be in quadrant 1 at pi over 6, and then we're going to add plus 2 pi k. And we know that will happen in quadrant 2 at 5 pi over 6 plus 2 pi k. Over here we have sine t equaling -2. I know the graph of sine of t. It has a range of -1 to 1. Sine t cannot equal -2, so our only solutions are those two equations. Oh, don't forget, k equals an integer. I hope you're all doing well. Have a great day.